Theorems are the building blocks of mathematics. Mathematicians use theorems to establish truth, develop their understanding, and build on pre-existing knowledge. Theorems are statements that have been proven by logical arguments. One of the most popular theorems is the Pythagorean theorem, where Greek philosopher Pythagoras discovered the length of the hypotenuse squared is equal to the sum of squares of the other two sides. However, to what extent can we trust theorems? What if a novel mathematician came in one day and in some way proved that this theorem was false? Impossible to believe, right? Mathematics, theorems, objective truth can never have contradictions. Well, that's what most mathematicians thought.
Gottlob Frege was a German mathematician, logician, and philosopher. He too held the belief that mathematics solely relied on logic and was unable to contain contradictions. Frege wanted to prove this by deepening mathematics and finding its core. Think of the whole of mathematics as a tree, with theorems being the leaves and the branches of that tree. As we work our way down, we begin to reach the roots, or the fundamental proof behind each theorem. These are called axioms. Axioms are the statements that are considered true or correct, indisputable in their origins. Frege essentially tried to axiomatize mathematics and demonstrate logic as the foundation of math. His first step was to prove the very center of math, which was numbers. What exactly is a number? For Frege, numbers were extensions of concepts. In simpler terms, numbers are anything you can think of. The concept of 10 would be an extension of all things made up of the collection of 10 objects. This was Frege's general comprehension principle. In the end, these were his findings he published in his book The Foundations of Arithmetic in 1884, until a certain British man came along and changed the course of both philosophy and mathematics.
Bertrand Russell was an English mathematician and philosopher. In June 1901, he found inconsistencies within Frege's work and communicated it to him through a letter in 1902. Frege was distraught. What exactly was the problem? To identify it, let's first take a brief look at set theory. You see that car? That car can be in a set labeled all the cars currently in London, Ontario. You see that building? It can be in a set called the really cool buildings. You see, a set is a collection of unique items. A set can even contain no elements, or even just one element. Sets can contain sets within themselves. Subsets within sets? That's fine too. But an interesting fact is that sets can also theoretically contain themselves as well. The set of all students at CCH would contain every student as a member, but it wouldn't contain itself because it is not a student. However, imagine a set of all things I am currently thinking of. If I start thinking about that set, it would belong in its own collection. All these rules are eligible because they are based on unrestricted composition, meaning you can make a set of anything you want. This was according to Frege's axiomized theory, but this led to a serious problem, as Bertrand Russell discovered.
Let's say we have a set called R, and this set contains all the sets that do not contain themselves. This set would include the all the cars currently in London, Ontario set, and all students at CCH set, and etc, etc. The critical question Bertrand Russell came across was that this set, R, the set that contains all the sets that do not contain themselves, does the set R contain itself? Let's go through the possibilities. If R contains itself, then by definition, it should not contain itself. Hold on. If it doesn't contain itself, then based on its own rule, it must contain itself. This leads to an endless loop, an unsolvable contradiction. This is the paradox that Bertrand Russell encountered in Gottlob Frege's work.
Although this is a relatively famous paradox, it is extremely difficult to understand. This is because a person may not completely have a strong grasp on the concept and theories being explained. By analyzing the historical context, we can see how this can help gradually ease the learner into math. This goes to show how sometimes dividing multiplex concepts and illustrating their relationship can be an excellent way of presenting them to an audience.